Welcome to solverfy.
This is the answer to Chapter 19, problem number 47 from the Smith Organic Chemistry textbook. And in this problem, we're given these three molecules, and we're asked to order them from least to most acidic. And then we're asked to give an explanation as to why. And so this middle molecule here is going to be least acidic. And as far as why it will be least acidic, it's because the carboxylic acid is not substituted directly on the aromatic ring. The carboxylic acid is separated from the ring by one carbon. And so this carboxylic acid is not much different than any regular alkyl carboxylic acid. We don't really get the stabilizing effects of the aromatic ring. Okay, so that's the least acidic. So the intermediate acidity molecule is going to be this one. So intermediate acidity. And again, with the carboxylic acid separated from the ring by one carbon, we're not really going to get the same strong effect that we would if the carboxylic acid were substituted directly onto the aromatic ring. But we do have the nitro group on the ring, and so there is going to be some inductive electron withdrawing effect. And so this molecule will be somewhat more acidic than the middle molecule here, the least acidic molecule. Oops, I should say least acidic. And then so the first molecule is going to be the most acidic, and it's going to be the most acidic for two reasons, really. So the carboxylic acid here is substituted directly onto the ring, and so we have all of the possibilities of drawing resonance structures where we can okay. So I'll actually just draw this resonance structure. So the electron withdrawing effect of the paranitro group is going to increase the acidity here. But the other thing, and let me move these over, okay, is without drawing every single resonance structure that we could draw here, there is a resonance structure once this is deprotonated. So let me go ahead and deprotonate this. So it'll look like this. Negative charge there. So there is a resonance structure that we can draw where this molecule is going to look like this. So we would obviously have to move through some resonance structures in between, but there is a potential resonance structure where we have our carboxylic acid here, well, our carboxylate ion rather here. So like that. And then we've moved the positive charge from our nitro group. Well, okay, you know what? Sorry, I'm trying to be as unconfusing as possible, and also trying to draw as little as possible. So okay, so the nitro group looks like this, right? And so this is how we conceive of a nitro group, where one of the oxygens has 2 bonds and 2 lone pairs and no charge, and the other oxygen has 1 bond and 3 lone pairs and a negative charge, and then the nitrogen has a positive charge on it. So this is what our deprotonated carboxylic acid would look like. And so we can draw a resonance structure for this where we can draw a resonance structure where both of these oxygens have negative charges. The nitrogen still has a positive charge. This oxygen still has a negative charge from being deprotonated, but we could move electrons like this. So these could go here, these could go here, and this bond could break. And so if we do that, we end up with a positive charge on this carbon. And so now we have a positive charge and a negative charge that are closer together. And so they're going to help to stabilize one another. And so for all of those reasons, that makes this first molecule here by far the most acidic. And that's the answer to chapter 19, problem number 47.